that is discrete time Fourier analysis. Okay, discrete time Fourier analysis. That means we are going to discuss about Fourier series analysis of Fourier series analysis of discrete time signal. Okay, so in sampling we have learned that we can convert continuous time signal by applying this sampling process. Okay, we can convert it to a discrete time signal, not like this. Okay, so what is the advantage of converting this signal into discrete time, this continuous time signal into discrete time? It is an additional process, no? But this process have some advantage. So can you tell one or two advantage why we are converting this continuous time signal into discrete time signal? Can anyone tell? So we can see that the one advantage is that we have already discussed. Okay, so if you want to save, if you want to store this signal in an electronic memory, in RAM or ROM, okay, so here you have infinite number of samples, no? You have infinite number of value. Okay, so this is not possible, no, because you have to have infinite number of RAM or memory. Okay, so what we can do is we can simply sample this. Okay, simply sample this and get some finite number of sample. Okay, we can get finite number of sample. Okay, finite number of sample. Then we can store it in a RAM from any memory location. No, so that is one example. Okay, so that means you can see that when we are processing or dealing with signal, normally we are dealing with signal through electronic circuit. No, nowadays those are digital electronics, digital component. Okay, so when we are processing and doing this signal processing in digital domain, okay, when we are processing and manipulating this signal in digital domain, it is a must, no? It is a must to sample or to have a discrete time signal, okay? Discrete time signal. Otherwise, it is very hard to manipulate, okay? So that is why we are converting that continuous time signal into discrete time, into a discrete time signal, okay? So that we can easily manipulate or process those signal through electronic circuit. Okay, so now you can see we have some advantage of the discrete time signal. No, so in most probably electronic circuit we come across with this discrete time signal. Okay, not continuous time signal. So we have to analyze this discrete time signal also. No, it is more important than analyzing a continuous time signal, I hope. Okay, so as in continuous time case, we know that the Fourier analysis is a very powerful tool to analyze a signal, especially in frequency domain. If we are doing a frequency domain analysis, this Fourier analysis is very strong tool, very powerful tool. Okay, so we have learned Fourier analysis already, okay, in case of continuous time signal, no? So we have already learned continuous time signal Fourier analysis, okay? Okay, so so what are the things we have learned there? Can anyone tell me? Basically, you have learned uh, to analyze periodic signal, no? Periodic signal and also non-periodic signal. Okay. So in periodic case, we called it Fourier series, Fourier series representation. Okay. And non-periodic case, we called it as what is non-periodic case? What is the term we used? Fourier transform, no? Fourier transform. Okay, so this Fourier series representation and Fourier transform we already learned for analyzing continuous time signal. Okay, continuous time signal, periodic and aperiodic, and also you can remember that these are deterministic signal. Okay, these are deterministic signal, not random signal. Okay, so we have done one discussion about Fourier analysis with respect to deterministic continuous time, periodic and non-periodic signal. Okay, so now we are going to extend it to discrete time signal. Okay, discrete time signal. Okay, so these are also deterministic signal. Deterministic signal. Okay. That means by that waveform equation we can characterize the signal, all the properties, all the behavior, any behavior of the signal we can characterize through this through the waveform equation of that signal. But if the signal is random, we can't do it. We have to approach some statistical analysis. No, we have already discussed those things. I hope you can remember. In our signal and system one, I have discussed this, not deeply, but surfacely we have discussed those things. Okay, so this is the deterministic discrete time signal. Okay, in same manner, we are going to learn discrete time periodic signal analysis, periodic signal. For that, we use Fourier series as usual, Fourier series representation. Okay, and also non-periodic signal, aperiodic signal. Okay, periodic signal. For that, we are using Fourier transform. Okay, Fourier transform. So we are discuss about discrete time Fourier series and some properties of that. Okay, and some properties. Okay, and also we hope to discuss discrete time Fourier transform and also some properties. Okay, so this is for, you already know that this is for periodic signal Fourier series, and this is for non-periodic signal. Okay, so in continuous case, same as in continuous case, we will start with Fourier series for periodic signal. Okay, so we will start Fourier series. Okay, so it is a new topic, fresh topic, so you can note down the important things and try to align with me and go. If you have any question, don't be shy, don't be afraid, just ask. Okay, okay, so we are going to discuss about Fourier series. of discrete time periodic signal. Okay, periodic signal. So I hope you that you can remember the Fourier series representation of continuous signal. Okay, so we can represent any continuous periodic signal as a collection of harmonics. Okay, so we are discussing about exponential, complex exponential Fourier series representation. Okay, complex exponential Fourier series representation. So in continuous time also we have discussed about this only, no? Complex exponential Fourier series representation. There are other type of Fourier representations there, but this is the most simple one and most popular one. So we mainly focused our discussion to complex exponential Fourier series representation. In this session, we do the same. Okay, we will focus only on complex exponential Fourier series representation. So I think you already can remember for continuous time we can represent any continuous time signal, okay, as a collection of harmonics, complex exponential harmonic like this, jk omega naught t. Okay, so so uh, so the same concept is here. Okay, so okay, same concept is here. We can represent any, so this xt is a periodic continuous time signal. Okay, same way we can represent any discrete time signal. Okay, so this n represent the samples. Okay, number of sample, we have already discussed these things. Okay, so xn, the discrete time periodic signal, can be represented as a collection of harmonics. Okay, in the same manner. Okay, so it is ck e to the power jk omega naught n. Okay, so this is t, this is n. Okay, because this n is the independent variable here. Okay, so this way we can represent any signal, any discrete time signal. So this is a discrete time signal as a collection of harmonic, weighted collection of harmonics, exponential harmonics. So this is the weighted coefficients. We called it Fourier series coefficients. No, simply we called it Fourier series coefficients. Okay, so in case of continuous time signal, you can remember that this k can goes from minus infinity to plus infinity. Okay, so if you can remember, you can sometimes you can memorize that some Fourier series have infinite number of harmonics. Okay, infinite number of harmonics. Can you remember that? Okay, we called a special name for this Fourier series. What is that? Can you remember any of you? If this Fourier series has infinite number of harmonics, what we called it? We called it what? Non-convergent Fourier series. Okay, we called it non-convergent Fourier series. That means the signal, the series is not converged. Okay, not limit to a single point. Okay, finite point. It is a non-convergent. Okay, so and also we can see that some Fourier series. Okay, in some Fourier series we have finite number of coefficients. No, okay, some Fourier series we have. So this is non-convergent Fourier series. Okay, non-convergent Fourier series. And some Fourier series we have, in that we have finite number of harmonics. Okay, so we can count the harmonics number of harmonics we can count simply. Okay, so what is that Fourier series we call? We call this convergent Fourier series. No, it is convergent to finite value, finite point. Okay, but you can see that when we are doing, when we are analyzing more, you can understand it. Okay, but for in case of discrete time signal, okay, in case of discrete time signal, all signal will be converged. Okay, all what we call it, all the series or the harmonic. Okay, we can say that the number of harmonics will be converged. Okay, converge. That means, in another word, we have always we have finite number of harmonics. Okay, this E, J, K, omega, this signal we called as harmonic. Okay, these are the harmonics. Okay, these are fundamental signal. No, so these fundamental signals sometimes we called as harmonics. Okay, I hope you can remember these terms. Okay, so anyone can guess why this is always the discrete time? Why? So anyone can answer why? Anyone can imagine why all discrete time signals, okay, Fourier series is converged. Why? What is the reason? Okay, so you can see that, okay, when we are getting the discrete time signal, it always have finite number of sample, no? So it is in finite length. Okay, finite length. Okay, always in finite length. So the Fourier series representation also in finite length. Okay, so that is one approximate reason. Okay, so so I think you can remember that. One thing I have forgot to tell you actually. Okay, another important thing, I think I have already informed this. I have already stated these things in signal and system 1. Okay, so if we have a continuous time signal like this, okay, so so this may be a power, okay, power with respect to time, okay, or any force with respect to time. Okay, say, okay, so you want to, okay, so maybe voltage with respect to time. Okay, so anyway, so here it is changing, no, with respect to time it is changing, and for a reason you want to get all this point, the summation of all this point. Okay, so how can you do it? So if this is if this time is t, okay, 0 to t, how can you do? How can you find the summation of all these points? Okay, so you have that this point, 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 this point, like this. Okay, but you can see that here we have infinite number of points, no? So we can't simply add them one by one. So what we have to do? You already know the answer. So can you tell what we have to do? You have to integrate, no? You have to integrate. You have to integrate this xt with respect to t over this period. Okay, over this period, 0 to t. Okay, then you can find, you can have the all points can be added. Okay, so in continuous time case, you have to always, you have to do the integration if you want to find a summation. Okay, if you want to find the summation, you can't simply do it. You have to do it through a integration. Okay. But in case of discrete time signal, okay, but in case of discrete time signal, say here we have some value here. Say these are some voltage value or temperature value or something. Okay, with respect to time. Okay, so here we have 2, here we have 3, 5, 6, 7, 8, 9, 10, like this. Okay, so if you want to add this point, okay, do you want to integrate it? In case of this sampled version, if you want to add these things, do you want to integrate or not? Just tell me yes or no. You no need to integrate, no? So you can see that you can simply add this point together. Okay, this 1, 2, 5, minus 6, minus 7, you can just add it there. Okay, like this. Okay, that means you have a summation here. Okay, summation. This point may be from say this point is xn or something. Okay, so xn you have. Okay, so you have to sum this point. Okay, this point from here to here. Okay, say this is 0 to n or something. So you can add them 0 to k or something. So you can add them simply. Okay. In case of continuous time signal, we have to integrate it. In case of discrete time signal, we no need to have to integrate. We can simply add all point together. We can get the summation. Okay. So I hope you get it. Okay, you got it. So let's again come to our discussion. Okay, so keep those in mind. Okay, so now you can see, you maybe remember that in case of continuous time signal, to find the coefficients, what we simply do, we have to integrate it, no? And you remember, we have to integrate it through one period. Okay, one period xt e to the power minus j omega kt. Okay, so you have to integrate this. Okay, to find the coefficients. But here, to find the coefficients, okay, in case of discrete time signal, to find the coefficients, okay, to find the coefficients, you no need to uh, integrate it. You can simply, it is very identical to this one, okay, 1 by t is there, okay, so 1 by, this is period measured in time, okay. In case of discrete time signal, it is number of sample, no, measured in value. It is a value 1, 2, 3, 5 value, okay. But you can, you may remember that this point we can map with time, okay. Okay, how it map with time? NTS, no, this is the time point related to the end sample, okay. So so here the period is time, here the period is number of sample and 1 by n. Instead of integration, we can have the summation here. Okay, integrate of this instead of this integration, we can have the summation here in case of discrete time. Okay, in case of discrete time, this is discrete time. Okay, so we have say here k, sorry, n. So we have to evaluate this through n, no, we have to evaluate this through n. Sorry, in case of continuous time, we have to evaluate this integration within one period. Okay, within period, one period. So we have to evaluate this one also within one period. That means within the number of samples. Okay, so if I start it with 0, the number of sample will be n with n minus 1. Okay, so here I have evaluate this within one period. Okay, so simply I have, okay, see here xt e j k omega naught t. So here we have xn e minus jk omega naught n. Okay. So this is the Fourier series representation for discrete time signal. Okay, discrete time signal. So I again write it. You have to keep remember this thing. Okay. So I will write it. Okay. So what is that? Fourier series representation for discrete time signal. Okay. So if the time signal is xn, it should be periodic. Okay, periodic. Okay. And here xn equal to, okay, sigma. Okay, here also we have finite number of sample 0 to n minus 1. Okay, is equal to 0 to n minus 1. And have ck e to the power j k omega n. Okay, jk omega n, and the coefficients can be calculated as ck 1 by n naught. Okay, sigma k is equal to 0. Okay, n minus 1. Okay, n minus 1 xn e to the power minus jk omega naught n. Okay, so I think you can remember that when we are evaluating the zeroth coefficient c naught, okay, in case of continuous time signal, okay, we have to integrate on only this xt, because e to the power jk omega naught t, when I apply k here 0, e to the power 0, it will be e to the power 0 and it will be 1. Okay, so we have simplified this. We can simply integrate this within the period, and with respect to dt, we can find the zeroth coefficients, and here also we can find the zeroth coefficients 1 by n naught sigma within period. Okay, only xn. Okay, no need e jk omega naught n, because k is 0 here. So e to the power, this whole terms will be 0, e to the power 0, and it will be 0. That will be 1. Okay, so c naught can be evaluated to this. Okay, so this is the Fourier series representation. And one thing I forgot to tell you, that this omega naught, what is this omega naught? That is the fundamental period, and fundamental period is what is the fundamental period? This is omega naught is fundamental frequency. Okay, and if the fundamental period is n naught, it is equal to 2 pi by omega naught. Okay, this also you should keep in your mind. Okay, so we will do some example. Okay, we will do some example. Okay, so we will first, before going to the Fourier series representation, we will try to find the period of discrete time series. Okay, so you know that the condition for periodicity is t plus capital N, sorry, x t plus capital T is equal to xt, no? Okay, so this t is time and this t is the fundamental period. This is for continuous time. Okay, in case of discrete time, it is n plus capital N x n. Xn plus capital N should be equal to xn. Okay, this is shit. Current again. Sure. So we have a power loss. Okay, so actually I'm using external monitor because my monitor is not working. Okay, so anyway, so have a power will be okay. Quickly they will on the generator. Okay, so I just have a 5 minutes and take a look at what we have learned. Okay, and try to map it with the continuous time domain. Okay, because we are now expert in continuous time domain. We are still not familiar with the discrete time signal. So try to map it. Okay, and try to understand what is going on there. Okay, so give me a minute. Okay. Hello, hello, team. Huh? Hello, can you hear me?
Yes, sir.
I have a power cut. Now it is okay. So So, I will share the screen, okay? Okay. So we will